All right. Well, it's Thursday, the day after the exam. Hopefully, you did well on last night's exam and you're feeling pretty good right now, confident as we move in to the last few weeks of the semester leading up to the final exam. So, in the remaining lecture time, what I'd like to do is tackle chapter 21. Chapter 21 is all about electrochemistry, and it really it is part of the core 1308 curriculum. So, we really need to cover this chapter in its entirety. It's a really important part of chemistry. It's practically very interesting as well. I think that you'll find it pretty enjoyable. Okay. So what are we going to do in this chapter talking about electrochemistry? Well, we're going to return to the idea of oxidation reduction reactions. These are called redox reactions for short. It's kind of an abbreviation. We're going to learn about them here in this first video, and really they play a key and central role throughout chapter 21 because all electrochemistry is rooted in these redox reactions. And we have to start there, get a very good understanding of what these reactions are, some key vocabulary and terminology, and then we'll move on from there, okay? So that's where we're going to start in this first video here Thursday. Now, what are we going to do with that, okay? Well, the first thing that we're going to try to do in this first video, I'm going to break it into several videos just to kind of keep things manageable. But here in a few minutes, we're going to get at balancing redox reactions, which sounds like a pretty easy skill. But it's a crucial skill. But it's actually a little bit more difficult or a little bit trickier than usual balancing reactions. And the reason why is because we're going to have to balance these redox reactions not only for mass, like we learned about in Gen Chem 1, but we're also going to measure them or balance them for charge. In other words, just like we can't create or destroy mass, we can't create or destroy electrons. The electrons that are transferred in these redox reactions have to go somewhere. We have to account for them. So we're going to learn how to balance these reactions. And this is actually important. We're going to learn to do this in both acidic and basic solutions. Usually when you're asked to balance one of these reactions, it's specified which one you're dealing with. And I'll show you how to do both here in this video this afternoon, okay? So that's going to be a key learning objective for the chapter. Now, what else are we going to do in this chapter, okay? Well, we're going to want to learn how to predict what's been oxidized, what's been reduced. We're also going to talk about oxidizing agent, reducing agents here in a few minutes. I want you to know those vocabulary words and be able to predict from a balanced chemical equation what's been oxidized, what's been reduced. Key and crucial skill as we'll move through this chapter. So we're going to tackle that here first, okay? Then from there, once we get a good handle on these redox reactions, we're going to learn how to harness these redox reactions to do some electrical work for us. This is where things start to get pretty interesting, okay? Because we're going to learn how to make what's called a galvanic cell or a voltaic cell. That's essentially a battery. So we're actually going to learn how to make batteries out of chemistry here in this chapter. We're also going to at some point consider electrolytic cells. Electrolytic cells are a little bit different because in an electrolytic cell, the key chemical redox reaction is actually non-spontaneous. And that's actually the difference between galvanic and electrolytic. In a galvanic cell, the process is spontaneous. But in an electrolytic cell, the process is non-spontaneous. So to make this reaction happen, we actually have to actively apply an electric potential or voltage to some electrodes to drive the process to occur. But if we do that, we can get a reaction occur, and this is an electrolytic cell. You can actually split water into hydrogen and oxygen that way, okay? So we'll talk about electrolytic cells. Then at some point, we're going to talk about standard cell potentials or standard cell voltages, how we can calculate those. It turns out it's not too difficult. We're just going to use a table of standard reduction potentials to help us. And way back the first day of class, I gave you all an equation card. Maybe you still have that in your notebook or whatever you've got. That equation card actually has a long list on the side. I think it's opposite the equations as I remember. But there's this big table of standard reduction potentials that I included there. We're actually going to use that table now because it's a list in order of given materials' tendency to be reduced. In this chapter, we'll see how a chemist might use that. Then we're going to be able to predict whether or not a given redox process is spontaneous or not. We can actually do that from the standard cell voltage. It's very, very easy as it turns out. And that standard cell voltage is going to tell us a little bit about what the value of the equilibrium constant or the Gibbs free energy change for the reaction is. There's some equations that we can use to interrelate those three things. We'll talk about that. We're going to talk about another equation. This is important. It's called the Nernst equation. The Nernst equation allows us to predict cell voltages under non-standard conditions. All right, so if we're working under non-standard conditions, we don't know what that means yet, but if we are under non-standard conditions, we're going to use this Nernst equation. That'll be an important equation for us for working problems. And we're going to learn about electrical current, electrical potential or voltage, what those things are, what they kind of relate to, electrical charge as well. Learn about measurement of those in this chapter and how we can relate the measurement of those items, those physical parameters, with the concentration of an analyte or how much of an analyte or substance might react, okay? So we're going to get into that once we get into a little bit more quantitative aspects of electrochemistry. Now, before I move on, we only have limited lecture time, okay? So I did want to call your attention to one task I'm going to ask you to complete on your own down here at the bottom. I'd like you to read the section on batteries and corrosion in the book, your textbook. It's between about pages 968 to 974. Go ahead and do that on your own if you would, please. I think that will be very helpful. It'll save us a little bit of time. And it's very interesting content. I think you'll find it interesting to learn how batteries are built. And also corrosion. You think about, many of you may kind of live out on a farm or something like that. If you leave items outside, they might start rusting or corroding. And that's what we mean by corrosion. It's actually the process of oxidation. So when we say corrosion, we're basically talking about oxidation. Usually it's some metal that rusts or something like that, okay? Well, there's actually corrosion protection. There's a strategy that you can employ practically in your life to prevent corrosion. Galvanization is an example of that. And this section of your textbook basically outlines how to do that. So it's practically very interesting, okay? So I'm going to motivate you to read that by just giving you that little teaser. All right, so this video introduces us to redox chemistry. Now, I think everybody in this class has seen redox chemistry before because it does come up in General Chemistry 1 in 1307, okay? So because of that, I'm going to consider this essentially kind of a bit of a review for us, all right? But it is super important that we master this content before we move on to other aspects of Chapter 21, or you could find yourself lost really quickly. And of course, I don't want anyone to do that. So let's spend a little bit of time on this. If you already remember this, that's great. If you don't, maybe it will resonate with you and we'll master this content and then we can move on. All right, so where do we need to start? Well, the first thing that we need to do is define what we mean by redox reactions. Now, redox, you probably see that thrown around a lot, and of course we will in this chapter, okay? But it's basically an abbreviation. It's an abbreviation for a type of reaction, which is a coupled reaction called a reduction oxidation, or likewise an oxidation reduction reaction. These overall chemical processes can be broken down into two sub-processes. Of course, one is going to be the oxidation, and the other one is going to be the reduction. So this is an abbreviation. We can use this term redox. But redox reactions are always oxidation and reductions. They're coupled together, okay? One thing's oxidized, one thing's reduced. Now, how can we tell the difference, and what are some key aspects of this, all right? Well, the first thing that I want to impress upon you is this first statement up top. In a redox reaction, electrons are transferred between reactants. Electrons are transferred, and this is super important. Super, super important. Because when we make a battery, all that we're going to do is we're going to allow this electron transfer to occur, but not directly between materials. We're going to force the electrons to flow through a wire or a circuit where they can do work for us. And that's how we're going to make a galvanic cell. It's a chemical process that involves transfer of electrons. We just force those electrons to flow through a wire and do some work for us. But the key idea behind all redox processes is that electrons are transferred, and that's going to be super important, okay? Now, let's master some other concepts in vocabulary. Oxidation and reduction. These are another key terms, all right? Let's talk about oxidation first. Any substance or atom which loses electrons as a result of one of these redox reactions has been oxidized. Alternatively, an atom that gains electrons is said to be reduced. Okay, so you want to memorize this vocabulary. It's very important, and we're going to harp on this here more in a few minutes. But if something loses electrons, it's been oxidized. If something gains electrons, it's been reduced. We'll come back to that, okay? Now, just to give us first glance at this, let's look at this reaction right here. This is an example of one of these redox processes. Something's oxidized, something's reduced. Now, if we look at this and specifically how the reaction works, let's break it down. That's done below the green text. In one part of the reaction, a sodium atom might be stripped of an electron or give up an electron to form sodium plus one cation. Now notice the electron is listed as a product in this reaction. The electron's given up, isn't it? The sodium atom has lost an electron. This is oxidation. Now, on the other hand, in this overall balanced chemical reaction, it looks like we take two of those sodium atoms and we react it with one molecular chlorine unit, or Cl2, to make table salt, NaCl, 2 copies of that. Well, what happens with respect to the chlorine? Let's key in on that. Well, we start with chlorine gas, Cl2. We add a couple of electrons to it to make 2 copies of Cl minus, chloride. Here, the chlorine gas gains the electrons. That tells us this process is a reduction because the chlorine gas gained the electrons. So in the overall chemical reaction up top, shown in the green text, what I want you to notice here, actually a couple things, right? But in this green text, don't we have both reduction and oxidation occurring simultaneously as this reaction proceeds? We do. And it turns out that's how all these reactions, when they're overall balanced, will always work. Something's going to be oxidized, something's going to be reduced. Hence the name, redox. You have to have both processes there. Now, another thing that I want you to key in on are these so-called half reactions. These are going to become important for us in a few minutes. But what half reactions are? Nothing more than us breaking up the overall chemical reaction into one for oxidation and one for reduction. So they're half of the total, or half reactions. One's for oxidation, one's for reduction. What I'd like you to start to notice about these half reactions, and this is kind of important, okay? For this bottom process with involving chlorine, notice that the electrons are a reactant here, and that's a characteristic of a reduction half reaction. The thing that's reduced, the electrons will be a reactant. Now, on the other hand, if you look at the dark blue reaction above, notice that here our electron is a product, isn't it? When the electron is a product, that's consistent with the other type of reaction, oxidation. So we can start to think of electrons being as products of a chemical reactant or ingredients in a chemical reaction, can't we? Another thing that I want you to notice here, this wasn't obvious at all because I didn't mention it before, but I'm going to return to it right now. Notice that our oxidation only produces one electron as written in this blue text, the dark blue. But our reduction requires 2, doesn't it? It's a bit of a problem. But notice we can correct that problem in the balanced chemical equation by just multiplying this first reaction by 2. We're actually going to do that here in a few minutes. But the point in me bringing this up is that when we're balancing chemical reactions involving oxidation and reduction, we must also not only balance mass, but we must also balance electrons or charges. More on that later, okay? But this is our first look into that. All right, so just to review then, oxidation is the process that occurs when something called the oxidation number of the element increases. I'm going to review that for you in a second. The element loses electrons. Compound might add oxygen, might lose hydrogen. And more importantly, and I guess most importantly and most generally, the half reaction will have electrons as products. On the other hand, the reduction occurs when the oxidation number of the element decreases. That's because the element gains electrons. It might lose oxygen or gain hydrogen. And again, most generally, the half reaction will have electrons as reactants. Okay? All right, so that's our first look into oxidation and reduction processes. Now, one thing that was mentioned here on this slide, and I'm going to return to this, and I purposely didn't talk about it much because, again, everybody may be at different starting spots here. But I do know that in 1307, or General Chemistry 1, wherever you took that at, you learned to assign oxidation numbers when you started to talk about redox chemistry. And we are going to get back to that right now, because that's another thing that's pretty important, these oxidation numbers. Oxidation numbers are very useful for redox chemistry because they also allow us to show or predict what substance has been oxidized or reduced. So looking back to this equation right here, I know that the oxidation number for this sodium in its uncombined form is 0. Likewise, the oxidation number for this chlorine is 0 because it's an element in its uncombined state with anything else, okay? But over on the right side, my oxidation number for sodium is the normal case, +1, and it's -1 for chloride. So another way to look at these redox reactions, I guess if you want to, and this kind of goes hand in hand with the transfer of electrons, is that if the oxidation number changes, that's a surefire sign that we have a redox reaction. If the oxidation number changes, we've got redox reaction, okay? Got redox chemistry going on. Now, like it says at the bottom of this slide, okay? If the oxidation number of an element increases, notice the case for sodium. We go from 0 to +1. That's for sodium, right? The Na. If the oxidation number increases, the process is oxidation. Now, on the other hand, we could exhibit a decrease in oxidation number. Like look at the Cl2, for instance. It starts off at 0, and on the product side, it's -1. In such a case, that substance has been reduced. All right, so we can also track oxidation numbers. And you probably remember that, okay? Now, because we can track these oxidation numbers, and they tell us something about how many electrons are gained or lost, I want to make sure that you all are familiar with assigning oxidation numbers. I want to review this and remember that, or to report these rules one more time for how to do this. Because again, once we get into balancing these equations, this is a must-have for you, okay? It's a must-have skill. So to assign these oxidation numbers, like I talked about briefly there on that last slide, there are rules. And sometimes these rules are a little tedious to remember. Not only do we have to remember the rules, we also need to remember their order, as it turns out. because typically speaking, the rules at the top of this diagram that I'm about to talk about up here, these are the ones that are most important. They really always have to be honored. We can't ignore them. However, the rules down at the bottom, the less important rules, those are ones that sometimes maybe we can ignore if we are honoring a more important rule. So let's see what we mean by that. Before we do that, let's go through the rules and then I'll show you some examples. Rule number 1, this is real important. If you have an uncombined element, it's not combined with any other element, so it's an uncombined element in its native natural form, it's given an oxidation number of 0 by default. So in that previous example, I think we had sodium solid, right? Or Cl2. This is what we're talking about. It's not combined with anything else. So it's got a 0 oxidation state. Just an element in its uncombined form. Pretty easy rule to remember. Most people remember that one. The next rule, sum of oxidation numbers of atoms in a neutral compound has to equal 0. If you've got a neutral chemical compound, doesn't have a net charge, if you add together the oxidation number for each atom which makes up that compound, you got to get a 0. That rule can never be broken, okay? The next rule, the charge on a monatomic ion is the same as its oxidation number. So if you have one of these so-called monatomic ions, so basically just one atom that makes up an ion, right? Like lithium plus 1 or iron plus 3 or sodium plus 1, something like that. Singular monatomic ion. For such cases, the charge on the ion is the same as its oxidation number. So for instance, in that previous example, I said this Na plus 1 has an oxidation number of 1 plus. Easy enough, right? Easy stuff. All right, moving on. That was our third rule. The fourth rule, for polyatomic ions, the sum of the oxidation numbers of all atoms in the ion has to equal the charge for that polyatomic ion. So if you bind or bond together different atoms to make a polyatomic ion, and that polyatomic ion has some charge, like sulfates, for instance, SO4 2 minus. The charge on sulfates 2 minus. So what I'm saying is that if you add up the oxidation numbers for every atom in that polyatomic ion, you got to get 2 minus. And remember, we always assign oxidation numbers on a per atom basis. That's important to remember as well. Okay. Moving on to lesser rules now. In their compounds, metals, specifically metals from the group 1 of the periodic table, have an oxidation number of plus 1. Group 2 metals, like calcium, say for instance, have an oxidation number of 2 plus. Kind of their common charge state, right? For halogens, now this is the other side of the periodic table, like fluorine, chlorine, bromine, iodine, such like that, right? If you've got an anion of a halogen, they are usually in -1 oxidation state, or halide, I guess it should be, like chloride, bromide. Most always they're -1. There is an exception to this rule that we can see sometimes. If a halide is bonded to a more electronegative element, or if a halogen is bonded to a more electronegative element, usually another halogen, as it turns out, like chlorine and fluorine might react to form a compound. In such cases, the element which is more electronegative gets that -1. And the other atom that's involved in that compound gets whatever oxidation state you need to make the sum equal to the charge, basically, okay? So that's one example where there's an exception to the rule. Now, rule number 7, then, is the oxidation number specifically for hydrogen in its compounds when it's bonded with other things. Usually, hydrogen's +1. But there are some examples where there's exceptions to that rule. Hydrides, for example. I'll get back to that in a second. The least significant rule is the oxidation number of oxygen. In most compounds is -2. There are some exceptions, however, that are listed down here. Now let's talk about those exceptions and how we can reconcile these rules with the exceptions. Now, when I started this discussion, I mentioned not only do we have to remember these rules, but we have to remember their order. Some rules are more significant and more important to others than others, okay? So to help us demonstrate that, let's look at this compound, NaH, which is called sodium hydride, if you're interested. Sodium hydride. I could ask you to assign oxidation numbers for this compound, okay? And the last one's an E. He's not going to let me write it, looks like. All right, fair enough. Sodium hydride. Now, I could ask you to assign oxidation numbers for this compound. If I did so, what would you do? You might start off thinking, what? +1 and +1. But that can't be right, can it? Reason being is if you add those oxidation numbers together, you get +2. This is a neutral compound. It has no charge. So you'd be violating one of these really important rules, wouldn't you, if you did that? So this +1 +1, it cannot possibly be right. So what do? Well, we honor the most significant rules, and we make exceptions to the rule for the lesser rules, okay? So rule number 2 up top tells me that, boy, the sum of my oxidation numbers for a neutral compound have to equal 0. So if I add oxidation numbers together for hydrogen and sodium, I got to get 0, don't I? So I read down my list then from high significance to lower significance and see what I come across. So I'm reading it on, reading on, reading on, reading on. Let's see. This one seems like it might be important. In their compound, group 1 metals have an oxidation number of +1. Sodium is a group 1 metal, so it should have an oxidation number of +1, shouldn't it? But notice that I included the word metal here in my list of rules. That's important. We don't usually think of hydrogen as being a metal, right? And in fact, if we look a few rules later, down here, 7, we can see there's a specific rule listed for hydrogen. It tells us that usually hydrogen's +1, except when we make a hydride out of it. So it turns out in this compound, sodium hydride, to make the math work, we assign hydrogen the oxidation number of -1, and we give sodium the +1. In doing so, we've honored the more significant rules, 2, which is a very high significant rule, right? We've also honored 5. We kind of ignored rule 7. In other words, we took the highest 2 rules in our list to honor, and we forgot about this lesser rule. There's another example of a common compound that maybe you all even have in your house right now, or apartment, or wherever you're living. A very, very common example is H2O2. This is hydrogen peroxide. You can buy it at the drugstore in that brown bottle, right? Hydrogen peroxide. It's a 3% solution usually when you buy it in water. Now we know that this is a neutral compound, so if we add together all oxidation numbers, we got to get 0, don't we? So if we add together the contribution of hydrogen and oxygen, we got to get 0. Rule number 2 tells us that. So we start again looking from top to bottom through our rules and seeing which ones apply, okay? We noted earlier that rule number 7 has to do with hydrogen, and it looks like rule number 8 has to do with oxygen, doesn't it? Rule number 7 tells us that each hydrogen should be +1. So since I have 2 atoms of hydrogen in my compound, I do 2 times +1. That's hydrogen's contribution, isn't it? Indeed, the oxidation number for hydrogen in this compound is +1. But what about oxygen? I mean, I've got 2 copies of it. And it seems like to make the math work, its oxidation number has to be -1. But my rule number 8 tells me that usually my oxygen's -2. So what gives, right? Well, to make this compound neutral, we have no choice. We have to assign the -1 to the oxygen because it's the least significant rule. It's rule number 8. And that's what we do to make it all work out, okay? All right, so not only do we have to remember these rules from top to bottom, because we need to remember which ones are important, we also need to remember how to apply them successfully, okay? Super, super, super crucial. So let's practice this a little bit, okay? I really think that this is an important start to this chapter, and I want to make sure everybody gets this. So I want to practice assigning some oxidation numbers now and figuring out what's been oxidized, what's been reduced. This is crucial stuff, okay? So let's look at these reactions. Some of them are balanced, some may not be. And what I'd like to do is assign oxidation numbers and figure out what's been oxidized, what's been reduced, okay? Let's try number 2 first. That's probably the easiest one. So we'll start with the aluminum solid. Is that an element in its uncombined form? Sure is. It's just an element. It's by definition got an oxidation number of 0. And if I look over on the far right, I see I have a similar situation for copper. An element in its uncombined form has an oxidation number of 0. I only have 2 other substances to contend with, don't I? The copper 2+ and the aluminum 3+. Now, these are monatomic ions, aren't they? And on that previous slide, we learned that for monatomic ions, their oxidation number is nothing more than their charge. So I can assign the copper a 2+ oxidation state. I can assign the aluminum a 3+ oxidation state. And I'm done. Now, what about the real question here? What's been oxidized and what's been reduced? Do you remember the definitions of those? What about oxidation? Was it the gain of electrons or the loss of electrons? Was it an increase in oxidation number or a decrease? These are things that we have to remember because soon we're going to need to be able to figure out what's been oxidized or reduced. Sometimes it's hard. It's hard to remember these things. So what I've done here at the bottom of the slide is I've listed a couple of these little mnemonic devices that people sometimes remember to try to keep track of things in their head. One that I really like is this oil rig business over here on the left. Okay, oil rig. We're in West Texas. There's lots of oil rigs, right? They're familiar sites, so maybe that's easy to remember. Well, if it is, that helps you because you can remember that oxidation is the loss of electrons and reduction is the gain of electrons. You might also choose to remember Leo the tiger. Leo says grrr. Leo, loss of electrons is oxidation, O, and gain of electrons is reduction. Okay, so a number of different ways you can remember this. Okay, maybe you can remember the Leo says grrr, or perhaps you use the oil rig. But either way, that kind of helps you figure this out. Okay, so let's consider aluminum in this first reaction then. Aluminum's oxidation number has gone from 0 to +3 as a result of this reaction, hasn't it? Its oxidation number increased. So did aluminum gain or lose electrons? What do you think about that? Think about it for a second. Go from 0 charge to 3+. Doesn't that mean that aluminum lost some electrons, specifically 3? Now, if that's true, what do we know about aluminum in this reaction? Hasn't our aluminum been oxidized? And since you always, if you have an oxidation, you have to have a reduction. Let's take a look at what's been reduced. Well, the only other reactant I've got here is the copper 2 plus. So my copper 2 plus goes from a 2 plus oxidation number to a 0 oxidation number, doesn't it? The copper 2 plus has been reduced. Its oxidation number has dropped. And chemically, why is that? Because it gained electrons. So the aluminum gave up electrons or lost electrons, and the copper took those electrons and gained them. Oxidation and reduction, right? All right, simple enough. Let's try a different example where maybe it's a little bit more difficult. I guess we can try this third one. In that third reaction, it looks like we've got some iron 2 plus going to iron 3 plus, right? So it looks like, isn't that an increase of oxidation number? So this must be our oxidation, which means that this other stuff needs to have been reduced. But can we justify that? Well, to justify it, we need to assign oxidation numbers, don't we? So let's take a look at that. How can we assign oxidation numbers? Well, we apply our rules. So this is where our rules come back into play. So in permanganate, MnO4, we've got two different substances, don't we? First one is manganese, Mn. We've also got oxygen. Now, I don't think we have a specific rule for manganese, Mn. In fact, it's a transition metal, and oftentimes transition metals can take on various different oxidation numbers. Okay? But we do have a rule for oxygen. In its compounds, usually oxygen has a -2 oxidation number. Now, there are some exceptions to that, like in hydrogen peroxide, we just talked about that. But this is actually not one of those exceptions. So each oxygen atom in permanganate has a -2 oxidation number. Now we've got 4 of those oxygens in this permanganate ion. And the overall charge of permanganate is -1, which means to me, this manganese actually has to be a +7 oxidation number to make this work. You say, okay, +7, how do you get that? Well, remember, the sum of all the oxidation numbers of all atoms in a compound has to equal the charge. Isn't the charge -1 on our permanganate? So I need to sum up the oxidation numbers and get -1. So if I take 1 copy of permanganate at +7 and add it to 4 copies of the oxygen each at -2, the math works, doesn't it? So that's how I can assign a +7 to that manganese. Now because of that, it makes it a lot easier to see how this manganese is reduced. Because isn't the oxidation number of this ion over here on the right +2? So I go from a +7 state all the way down to a +2. That's a reduction. So if I apply my rules that I learned about in that previous slide, I can then figure out what's been oxidized and what's been reduced. Again, that's a very, very key skill here, okay? Very key skill. You need to be able to know what's been oxidized and reduced before we can go any further with electrochemistry chapter, okay? All right, one more quick example. Let's try to work this one quick up top, okay? Now we got chlorine gas Cl2. Well, that's an element in its uncombined state. That's got a 0 oxidation number. What about I-? Oh, it's -1. It's a monatomic ion. Just like chloride over here is -1. Looks like I got H+. Oh, I made some H+. That's a +1. It's a monatomic ion. Now what about in water? Well, usually our oxygen is what, -2. Usually our hydrogen is +1. Does that work for water? I think it does. 2 copies of a +1 balances the -2. It's a neutral compound, so we're good. What about over here on the right then? We've got this ion triiodide. Oxygen's -2. That makes -6. So it looks like our iodine has to be +5 as a result. So what's been oxidized? What's been reduced? Well, our chlorine goes from 0 to -1. Looks like that's been reduced. What else do we've got? Well, H plus is +1 over here. It's +1 over here. That didn't do anything, right? Anything else? Oh, wow. Look at the iodine. The iodine went from a -1 to a +5, didn't it? That's a big change. So can't we say that our iodine has been oxidized because it's experienced an increase in the oxidation number? All right, so sure enough, we can identify things that have been oxidized or reduced. That's a key skill. One more key skill is identifying oxidizing agents or reducing agents, okay? The oxidizing agent is actually reduced during the reaction. The reducing agent is actually oxidized during the reaction. It's kind of confusing, but I like to think of it as the oxidizing agent is the substance which causes oxidation in something else. Thereby, it's being reduced. The reducing agent is the substance that causes reduction in something else. So it actually gets oxidized. So let's look at that middle example again, because it's kind of the simplest case, right? We said earlier that in this middle example, the aluminum was what? Oxidized, wasn't it? So because it was oxidized, that means that my aluminum is the reducing agent. It's the substance that causes reduction in something else. And that something else here is the copper 2+. Okay? So my aluminum is the reducing agent. So likewise, if we then consider copper 2+, the copper 2+ gets reduced to copper solid. We actually produce copper solid or precipitate copper solid out of this solution. So because it's reduced, it is our oxidizing agent. That's that material right there. All right, so simple enough. Again, it's just kind of vocabulary and identifying. All right, now what we'd really like to get into in this reaction, or in this video, is balancing redox reactions. We're going to use a method called the half reaction method to help us do this. So the reason why we spent so much time looking at these individual redox processes of oxidation and reduction, being able to identify them, is because ultimately we want to balance redox reactions, no matter how complicated they are. And some of them can get chemically pretty complicated. At least their reactions look that way. But they all involve transfer of electrons. Now, to balance them, we really need to be able to pick out what's being oxidized and what's being reduced, because we're going to have to separate the overall reaction into what's called half reactions, okay? Because our general scheme for balancing these reactions, the first step is we're going to take the overall reaction and break it down into one reaction for oxidation and to a second reaction for reduction. We take one overall process and separate it into the two redox component parts, okay? And then in the end, after we're done balancing most things, we're going to recombine things, okay? But we've got to identify what's being oxidized and reduced first. It's super, super crucial, okay? All right, so let's take a look at what an example problem might look like. It's down here at the bottom, and this is actually, it turns out, a pretty simple one. We're actually going to be able to balance this one by what's called inspection. But nonetheless, it'll kind of show us the overall thought process, and then in a second we'll work one in a more organized way that's much more complicated. But in this simple example, we've got aluminum and copper reacting. It's aluminum solid, copper 2 plus. So if we're assigning oxidation numbers, we'd say this aluminum 0, but over here it's 3 plus. This copper is 2 plus, so it's a 2 oxidation state, but over here the copper is 0. Now, could I break up this overall reaction into an oxidation and a reduction half reaction? I bet you I could, pretty easy. What's the oxidation? Isn't it the aluminum going to Al3 plus? And then on the other hand, my reduction is involving the copper 2 plus being converted to copper solid, or copper 0 oxidation number. So these are my two half reactions. Now, the next step in our half reaction method is going to be to balance each half reaction independently of the other one. We start by balancing for mass, just like we normally would. Do we have the same number of atoms of each type on both sides of the arrow? Now I'm looking at these reactions, and it seems like I've got one copy of aluminum on either side of the arrows. I've also got one copy of copper. So for mass balance, I'm good. I haven't created or destroyed atoms, I guess you could say, all right? But the thing is, for this redox chemistry, we also need to balance charge. We need to balance electrons. Now, if I'm looking at these reactions with an eye towards balancing charge, I'm not so sure they're balanced anymore. Because look, in both reactions, I don't have the same charge on both sides of the arrow. For aluminum, I've basically got 0 charge on the left, but I've got a 3 plus on the right, don't I? Clearly, this is not charge balanced. Similar situation exists for the copper. I've got 2 plus on the left and nothing or 0 on the right. I have to do something about this. I have to balance for charge. When we're balancing these half reactions, the way we balance for charge is we basically add electrons wherever are necessary to make charges balance. We add electrons. So what I'm going to do in this first half reaction is add 3 electrons to the right side. Electrons are our primary negative charge carrier. If I add 3 of them and I combine 3 negatives with this 3 positive, right here, 3 negatives, 3 positives, that makes a 0. Note that we have 0 on the left, and by doing that we come into charge balance. What do I need to do on the bottom reaction? You see a possible solution for my reduction? I need to make myself some more space. Because what I need to do, don't I need to add 2 electrons to the left side here? If I add 2 negatives to a 2 positive, I get it's neutral, which is the same as what I have on the right side of my arrow, don't I? So I add electrons wherever necessary to balance my charge. And that's a key step. What's cool about this step is notice that for my oxidation half reaction, aren't my electrons listed as a product? Because the electrons are given up in an oxidation. And in my reduction half reaction, my electrons are listed as a reactant because they're used to reduce my copper 2 plus. This will always be the case. One of your half reactions should have the electrons as a product. The other one should have the electrons as a reactant. You should always see that, okay? Now, what we'd really like to do is recombine or add these equations back together to generate our overall chemical equation. But we've got a problem. The first reaction produces 3 electrons. The oxidation produces 3 electrons as written, but the reduction only uses 2. So if I was to add these 2 equations back together, I'd have a bit of a problem. That first reaction makes 3, the second reaction only needs 2. Where does this other electron go? We can't have unbalanced electrons, right? We can't have imperfect accounting of either mass or charge in this case. So we have to figure out what to do about that. And it's actually a pretty simple solution. What we do is we multiply our half reactions by whatever integer is necessary to create the correct amount of electrons. So in this case, I'm going to cross multiply. If I multiply this first reaction by 2, and I multiply the second reaction by 3, I can make a common number of 6, basically, okay? 6 electrons. So if I multiply this first one just to show, I guess, let me get a little bit more perfect example. So to show this out, this whole thing is this first reaction with the aluminum. I'm going to multiply that by 2. So what that's going to do for me is I'll have 2 copies of aluminum, 2Al3+, but because I doubled the amount of reactants, I'm not going to have 3 electrons anymore. I'm going to have 6, aren't I? And in the second equation then, I'm going to multiply everything by a 2, or sorry, a 3, my bad. 3 over on the far right here. So what that means is I'm going to have 3 copies of this produced. And I'm going to have 6 electrons involved in this reduction. And 3 copies of my copper 2+, okay? So by doing this cross-multiplying bit, we get the same number of electrons produced and used. And as a result, we're able to then combine these two equations. 2 copies of aluminum plus 3Cu2 plus makes 3 copies of Cu solid and 2 Al3 plus. My pen's giving me trouble here. But you see what we did. We multiplied, or we balanced the equation for mass, and then we balanced it for charge to generate the overall balanced chemical equation. Now, in this particular example, it was pretty simple to kind of see what was going on, right? The aluminum is going to give up 3 electrons. The copper 2 plus needs 2 as written. You could probably reason out these values in your mind, okay, to balance this reaction. But for more complicated examples, it's going to be a lot more challenging, okay? We're going to see one of these examples here in a second. But before we do, I wanted to define for you a general framework for how we're going to balance these redox reactions. There is a series of steps, and I'm encouraging you to memorize these steps because it turns out they won't fail you. It's a really safe protocol for balancing these redox reactions. The first thing that we're going to do is assign oxidation states. You got to determine the element which is oxidized and the one that's reduced. Because the next step, number 2, is to break up the 2 half reactions into an oxidation and a reduction half reaction. We then balance each half reaction individually for mass, just like we did in that previous example. Now, when we're balancing for mass in more complicated examples, there's a stepwise protocol. And I want you to always follow that. The first step is balance elements other than hydrogen and oxygen. Everything else, balance that first for mass, or number of atoms on each side. Then, next, we're going to balance oxygen, but we're going to do so in a very strange way. We're going to add water molecules to whichever side of the equation that we need to balance the oxygen. Basically what we're saying is this chemistry that we're going to consider for our purposes all occurs in the aqueous phase. So water can participate in the reaction as a reactant or product. So we're going to add water wherever we need to balance the half reaction for oxygen. Just have to remember to do that. It's actually quite convenient. And then lastly, we're going to balance hydrogen by adding H plus wherever we need. Okay? Next, we're going to balance half reactions for charge. We're going to do this by adjusting the number of electrons as needed. We write the electrons as either a reactant or product, and then we adjust the number that we have by multiplication by some integer, such that the number of electrons in their oxidation and reduction half reactions balance out, cancel out. We then add our half reactions together in step 6, and we can double check to make sure that our reaction's balanced. So what I'd like to do now is just work through an example to show how this works. I'm going to give us this redox reaction down at the bottom of the slide, and then we're going to work through balancing it. Now, before I get into this problem, I want to define for you a specific set of conditions to look for. These problems are often balanced in either acidic solution or basic solution. It seems like a minor detail, but in fact, it's a little bit important to pay attention to that, because in acidic solutions, we've got lots of H plus around. But in basic solutions, we have a very low concentration of H plus. So when we're adding H plus in this step up here, it makes sense that you could add H plus as a reactant if the solution is very acidic, right? I mean, plenty of H plus there, it can participate in the reaction. But in a basic solution, that doesn't make as much sense. So the moral of the story is that we're going to have to pay attention if it's acidic or basic. And if it is basic, we're going to have to do some special steps at the end to get rid of this H plus that we add. And I'll explain that here in a few minutes, how that works, okay? All right, now with that said, what I'm going to do is I'm going to work this example problem to balance this overall redox process. And I'm going to do so within the framework of these steps. So when I'm working through this problem and showing you how to do this, I want you to keep looking back to these steps in your notes to keep track of what I'm doing each and every step of the way, okay? That's an important thing to keep in mind, because I'm really just going to follow these steps. All right, so I've devoted an entire sheet of paper here to help me with this, and I think I am going to need it, all right? Because what do I need to do first? Assign my oxidation numbers to figure out what's oxidized and reduced. So by now you know that I like to start with the freebies, right? So I've got a monatomic ion here and here, don't I? Monatomic ions are easy to assign the oxidation numbers to. It's just a charge on the ion. So the iron 2 plus has an oxidation state of +2, and it goes to 3 plus, doesn't it? So I can already start breaking up the half reaction involving those substances as iron 2 plus going to iron 3 plus. Now, is that my oxidation or my reduction? Seems to me that's my oxidation, isn't it? Because my oxidation number increased. All right. Now, with that said, I still have a little bit more work to do, because I got to figure out what are my oxidation numbers in this permanganate. Now, I actually already assigned these in the videos, or this video earlier today. We decided that oxygen has the usual rule apply, the -2, and that because of that, this manganese had to be +7, because the overall charge is -1. And remember, if you add up all the atoms in the compound, you got to get the charge. So +7 and 4 -2s make a -1. Now, because of that, what do we see? Well, the manganese goes from +7 to +2. Seems like that's a reduction. So right here out of the gate, I'm able to break up this overall chemical reaction into an oxidation and a reduction, half reaction. So I've already achieved that, haven't I? So where do I go from here? Well, my next step is to follow the protocol. The next step in the protocol is to balance for atoms other than oxygen and hydrogen. So I look at this top reaction involving the iron, and I note that I'm basically already balanced, aren't I? I've got one copy of iron on each side. I'm going to rewrite it to here to save myself a little bit of space if I can. So I got my iron 2 plus, I've got my iron 3 plus on the right. It's my oxidation. And I'm balanced for all other elements except for hydrogen and oxygen. In fact, there is no oxygen or hydrogen, so I don't even need to worry about that either. But what about my reduction? Well, I have my MnO4, my permanganate ion, and it goes all the way down to manganese 2+. Manganese is balanced. That's my first consideration. And then after I'm done with that, I move on to balancing all other elements, like oxygen and hydrogen. Well, if I'm looking at this, it seems like oxygen is out of balance for my reductive half reaction. I've got 4 copies of oxygen on the left and I've got none on the right. I don't know how I can fix this if I can't add anything. But remember in my instructions that we were talking about a few minutes back on that previous slide, I said that I could deal with oxygen by adding liquid water wherever I need. And I add as many copies as I need to balance. So because I've got 4 on the left, I'm going to add 4 copies of water on the right. And that brings me into mass balance for the number of oxygen atoms, 4 on each side. But in doing that, now I've added some hydrogen, haven't I? Specifically, I've added 8 copies of hydrogen. But remember, my rules or my protocol told me that I could fix that by adding H pluses. So by adding my water and my H pluses, I can bring oxygen and hydrogen into balance for this half reaction. Now this step is kind of strange, isn't it? Because in Gen Chem 1, you aren't supposed to modify what's reacting or what's being produced. You weren't supposed to add in different chemicals. But we're actually going to encourage you to do that here for balancing these redox reactions in aqueous solution. This is how the process works. So by adding in my water and my H pluses in that specific order, I can balance this reaction, really both of these half reactions, for mass. They're all mass balanced now. But are they charge balanced? Hopefully you realize that they're not. They're not charge balanced. I haven't talked about electrons or charge at all yet. I need to consider that now. So remember, how did we charge balance before? We added electrons, however many electrons we needed, to whichever side was necessary to achieve the charge balance, or equal charges on both sides of the arrow. Now I'm looking at that first reaction involving the iron up top, right? And what I'm really tempted to do here is to add 1 electron to my right side. And the reason why is because if I do that, I've got 1 minus added to 3 positives on that right side. So that right side would be a net 2 positive, which is the same as what I have on the left. Remember, I can only add electrons, and I add the n number of electrons, however many are necessary, to achieve charge balance. So by adding just 1 on the right for this example, I can do that. Now what about this second reaction, this reduction? Oops. Let me erase that and start over. In this reduction, I have 8 H pluses on the left, reacting with 1 permanganate to make manganese 2+ and 4 copies of water. Now if I add up the total charges on the right, I only get +2 from that 1 copy of manganese 2+. What do I get if I sum up all charges on the left? Well, the permanganate's -1, but I still got 8 pluses, so that's 7+ total. My math is correct, right? So we go from a 7+ to a 2+. That's a huge charge imbalance. How can I correct this? What if I add 5 electrons to my left? Then it's 2+ to 2+. So that's what I need to do. So let me see if I can create some space for that. I have to erase this stuff. So to make my charges balance, I need to have 5 electrons combined with 8 H pluses and my single copy of permanganate. Now if I do that, I've got +2 charge on both sides of the arrow, and that reaction is now charge balanced. So I'm following my protocol. Let's go back just to make sure, okay? Did I assign oxidation states? Yes, that was my first thing I did. Did I write out the unbalanced oxidation and reduction half reactions? Yep, sure did. That's where I broke it up into the two half reactions, right? Just looking back real fast. One was for the iron, and that next half reaction was for the permanganate. Two half reactions, oxidation and reduction, right? So we got that. Did we then balance the half reactions by mass? We started by every other element other than hydrogen and oxygen. We balanced oxygen by adding water. We balanced H by adding H pluses wherever necessary. We just got done adjusting the number of electrons to make the charges balance, okay? All right, moving on. So next, now what we need to do is balance or work towards recombining all of these equations back together. And by doing that, we have to look at the electronic counting a little bit more, okay? This is my chemical change arrow. It looks really bad. All right. Now we want to combine both the oxidation and the reduction half reaction back together at this point. But we can't. We have a problem. Because on the right of the first reaction, I've got one electron being produced. But on the left of the second reaction, I need 5 to make that reaction go. So my oxidation only gives me 1 electron, but my reduction requires 5. So I cannot combine these reactions yet. I have to do something else. And what that something else is multiplying that first reaction by 5. All I'm doing is I'm changing the number of copies which are involved in the reaction, multiplying it by 5 times as much. But if I do so, the resultant reaction involves 5 electrons, not 1. And the beauty of that, then, is the 5 electrons which are produced can be used, for the oxidation, can be used in the reduction, combining with 8 copies of H+, and my permanganate ion, which was originally present, to make manganese 2+ and 4 copies of water. And now I can combine these two equations. It's my plus sign. I can combine these two equations because I produce 5 in my oxidation, I use 5 in my reduction, and as a result, I can combine the equations and all of the reactants and products come down to the final balanced equation. This is my 4 copies of water, okay? You'll see that? So we balanced for mass, then we balanced for charge. Each individual half reaction. And then in this secondary step, we multiplied by an integer, whichever integer was necessary. Here it was 5, such that the number of electrons produced by the oxidation are the same as the number of electrons required for the reduction. When we did that, we could cancel out the electrons we make and use. There's no net change in the number of electrons. In other words, we produce what we use, and then we come up with the overall balanced chemical reaction. Is it balanced for iron? 5 and 5, yes. Is it balanced for manganese? 1 and 1, yes. Is it balanced for oxygen? 4 and 4, yes it is. Is it balanced for H? 8 and H, yes it is. Is it balanced for charge? Well, it better be. Let's see. On the right, I've got, 15 positives from the iron, I've got another 2 plus from the manganese, and water's neutral, so that looks like it's 17 plus over here. What about on the left? Well, I've got 10 pluses from 5 copies of iron 2 plus. I've got another 8 plus from the H, and then I've got 1 minus, also 17 plus. It's charge balanced. Okay, so this reaction checks out. And this then is our balanced chemical reaction for this redox process. Now, one detail. What I've just shown you how to do is to balance a redox reaction for one specific set of conditions. The acidic case. Remember back a few minutes ago, I said we could do this for acidic or basic conditions. What we have right here is the answer for the acidic conditions, but it would not be an acceptable answer for the basic conditions. The reason why is because of this right here on the far left. Notice that we have the H pluses present as a reactant, don't we? Would it make sense that this reaction would occur in basic media where there's not a lot of H plus to be present? I'm not so sure that that makes a lot of sense, right? And just think about that for a second. If you're in a basic media, you don't have very much H plus. So could you really use it as a reactant? It doesn't make sense. So we have to do something to fix that. So while this answer works for an acidic solution, and it would be the preferred answer for an acidic solution, not going to work so good for a basic solution, okay? I got to rewrite my 4H2O over here. I accidentally erased it. All right. So what are we going to do to balance for basic solution? It turns out we do what I'll call a trick, okay? We start off the problem, even if it's in basic solution, we know that from the onset. We start off balancing, just like we would for acidic solution. There's no difference, okay? Until we come to this last step, where we're at right now. What we do is we take the result of the answer for the acidic solution, and we get rid of these H pluses. The way that we do that is we add hydroxide ions. We add the quantity needed to basically titrate off the H pluses. So in this case, I'm going to add 8. I'm going to add 8 OHs. And when I add those 8 OHs, instead of having 8H plus, I'm going to add the 8 OHs, and I'm going to titrate this H plus, make H2O. And everything else on the left is going to come down and remain the same for right now, okay? Now, since I add those 8 OHs to the left, I also need to add them to the right. Can't forget about that. Okay, so because I added 8 on the left, I also had 8 on the right. But then after that, everything else also comes down. So my 5 Fe comes down, Fe3 plus. Running out of space. As is my Mn2 plus. As does my water. And I had 4 copies of that. Makes sense? All right. Now the next thing that's happened is I've made this water on the left. And I also have this 4 copy on the right, right? Remember, chemical formulas only really want to show the overall net change that occurs. So I do a little bit of canceling out. I say my net change is the use of 4. So I had 8 being used, but then I got 4 back. So I'm basically going to erase this 4. and then only account for a net change of 4 on the left. And everything else comes down. So my 8 hydroxide, my 5 Fe3 plus, my manganese 2 plus, all of that comes down, and now my 4 water is gone, right? So then this would be my accepted answer for basic solution. So if you're balancing an acidic solution versus basic solution, the answer that you get is going to be different, right? I guess that makes it a little bit tricky. But the answer here would be acceptable for acidic solution. But for basic solution, I need to choose this response down at the bottom, where I get rid of those H pluses, okay? So that's the difference. I mean, what we did is we just added this one step on where we added the OHs at the end for basic solution. And that's just how these problems tend to be worked, okay? All right, so just to kind of summarize, so I showed you how to do it in basic solution. Now just to kind of summarize what we talked about here in this video, we learned about redox reactions. They involve transfer of electrons, oxidation, and reduction. You're always going to have both processes, okay? That's very important. We learned how to balance redox reactions, identifying what's being oxidized and reduced. It's a key learning skill for this chapter. We need to be able to do that to move forward. And we also need to understand that electrons are being transferred here. That's another important conceptual idea behind these redox reactions, okay? So I'm sure that you're going to see example problems in your online homework here to practice this balancing process. Practice that a little bit. Make sure you get it down. You're likely to see a question like this on the next exam, I would say. Just having to balance a reaction, okay? And to encourage you on, always follow this stepwise process. I think it really is very useful and it's not going to fail you. So back to those steps again, the ones that are here outlined on this slide for balancing redox reactions. I mean, this stuff is really, really important. You'll want to practice it a little bit, but it's nothing that each of you cannot master. All right, see you in the next